All right, so this is the first set of notes from the last unit in the course, which is the most algebraic of all the units, covering chapters 3 and 4. And so I want to start with something that I hope sounds familiar, which are square roots and cube roots. And even before that, I want to start with some terminology reminding us what a factor is. So if I look at this equation here, 2 times 5 equals 10. The 2 and the 5 are what we call factors. So 2 is a factor in this case, 5 is the factor. And when you multiply factors, you get a product. So 10 is the product. And this is just terminology. So again, factors are what multiply together. Product is your, I guess in this case, what you get when you evaluate. And so for the equation on the right, A times B equals C. A is a factor, and B in this case is a factor, and C is your product. So mostly, I just want to remind you what a factor is. And we're going to hear that phrase a lot actually in this unit, especially by the end. So a perfect square is the product of two equal factors. And just one of these factors is called a square root. So for example, 6 times 6, 6 and 6 are the factors. In this case, the 36 is what we call a perfect square because it is the product of two factors out of the same. And that term should definitely sound familiar. And each of these 6's here, these are the, each of these, because of the same, these are the square root of 36. Right? Either of these. Because it's the same thing. And so we can summarize this equation, we can summarize what I've just said by saying the square root of 36 equals 6. All right, and that's it. We don't have to stick with just numbers we know. We can use variables. So a times a equals a squared. So in this case, a squared is the perfect square. And each of these a's is the square root of a square. And so I can summarize this, what I've just said, by writing the square root of a squared equals a. A squared being the perfect square, a being the square root. All right, that's it. If we understand what a perfect square and what a square root is, then a perfect cube should also sound familiar and is the same idea. It's when we have a factor that's the same 3 times. And so in this case, the 64 here is a perfect cube. And each of these 4's is the cube root. Each one. So each of these is the cube root of 64. And I can write this, what I've just mentioned here, as using this symbol here. The cube root of 64, in this case, equals 4. That's it. We can apply this to any number. A can be any number here. And so in this case, again, a cubed, a to the power of 3, that is my perfect cube. And each of these a's is the cube root. And all of this here I can summarize by saying the cube root of a to the power of 3 equals a. All right, most of this should sound familiar, although there's a decent chance you never looked at this involving variables. But I know you've heard about square roots and cube roots before. They go back to at least at the very latest grade 8. All right, next I want to review something else, which is what we call prime factorization. And this goes back to elementary school. And for this, I want to just first remind you what prime factorization is, and then show you how we can relate it back to square roots and cube roots. So if I want to find the prime factors of 216, I want to break up 216 into factors, numbers that multiply together to make 216, over and over again, making all these branches where the numbers get smaller and smaller until all I end up with are prime numbers. So for example, 216 is a pretty big number. I don't know my times tables so well up to 216. But I do know it's an even number, so 2 times something must equal 216, and that something must be half of 216, so that's 108. Now 2 is a prime number, so that branch comes to an end. 108 is not a prime number. Now 108 is an even number. I could break it up to 2 times something again. However, if you know your 12 times tables, which I kind of hope you do, you may know that 12 times 9 is 108. So just for something different, I'm going to go 12 times 9 here. Now neither 12 nor 9 is a prime number, so I can break each of these up more. 12 the same as 4 times 3. 3 is a prime number, so I'll stop there. 4, though, is definitely not, because 4 is the same as 2 times 2. Each of those are prime numbers, so those branches have come to an end. All I've left is my 9 over here. 9 is the same as 3 times 3. So hopefully this sounds familiar. This is this would be a concept from a grade 6 class probably. So what does this tell me? Well, this tells me that 216 is the same as 2 times 2 times 2 times 3 times 3 times 3, my n branches in any order. So I can maybe write this right here. I can say 216 is the same as 2 times 2 times 2 times 3 times 3 times 3. Okay? Well, remember when you're multiplying, the order you multiply doesn't matter. So I can rearrange these 6 factors, 3 2s and 3 3s. I can rearrange these 6 factors in any order I want. If I rearrange them like this, the 2 times 3 times 2 times 3, right, if I rearrange it like this, the 3 little groups like this that are all the same, I can now see that 216 is a perfect cube, because I can see that 216 is the same as 2 times 3, 3 times. And so I can also say, if I want, say this is the same as 6 times 6 times 6. Or I can say the cube root of 216 equals 6. And I'm just trying to show you how by looking at the factors we can understand cube roots and square roots. And I took a bit of grade 6 math quite quickly, but all of this here is grade 6 math. And then use that to look at the factors. And again, all these parts I've highlighted in yellow and blue are factors. And again, that's a phrase we're going to hear a lot. And again, all it means is something that multiplies into something else. All right. So now let's evaluate some of these things. That means calculate. And without a calculator as much as possible. So negative 3 squared, this literally means negative 3 times negative 3, which is positive 9. All right? And maybe because of the next one, I'm even going to write out what this means. This means negative 3 times negative 3, which is positive 9. The next expression does not mean the same thing. The next expression means something slightly different. There's no brackets. This means 3 to the power of 2, so 3 times 3, with a negative in the front. That's what this actually means. Or negative 3 times positive 3. Either way I look at it, this equals negative 9. So again, those brackets are really, really important. If there are no brackets, it's just 3 to the power of 2 with a negative sign in the front. If there's brackets, it means negative 3 times negative 3. Okay, so it changes where that negative is. And that's what brackets do. They change the order of operations. So always got to pay very close attention to that. 2/3 to the power of 2 just means 2 over 3 times 2 over 3. And what is actually quite easy to do, when you're multiplying with fractions, you don't need a common denominator. You just multiply the numerator together. 2 times 2 is 4. 3 times 3 is 9. There you go. Now, the next one doesn't have brackets. So this means only 2 to the power of 2 divided by 3. So 2 to the power of 2 is 4 over 3. So again, we got to pay attention to the details of brackets. Clearly, brackets change what operations are taking place in which order. In this case, all of these 4 questions all represent a slightly different sort of order of operations. Okay, that's with powers, squares, and cubes and whatnot. Here we have roots. And so the square root of 49, hopefully you don't need a calculator to know that is exactly 7. The square root of 9 times 16. I will say, if you actually go to your calculator and type 9 times 16, you get 144. Okay, which 144, if you did that, is a perfect square. The square root of 144, hopefully you know, is 12, because 12 times 12 is 144. However, well, there's nothing wrong with that. I want you to notice that I'll get the same answer of 12 if I look at it like this. If I break it up, the square root 9 times square root 16. If I look at these separately, I'll get the same thing. The square root of 9 is 3. The square root of 16 is 4. 3 times 4 equals 12. Okay, and so I just want us to realize that's not a coincidence. I can also, again, I'll write down what I had before. It's all the same thing. And just realize, again, that's not a coincidence. If you're multiplying, when you have something like this, if you can see your factors inside, you can square root them separately when you're multiplying together, or you can multiply them all together first. That's it. Let's look at cube roots. The cube root of 27, what times itself 3 times equals 27? That is exactly 3. That's it. You do want to become familiar with your calculator about how you can find a cube root when we need to find a cube root. But for this, I don't. If you know 3 times 3 is 9, 9 times 3 is 27. I don't need a calculator for that. And lastly, this, the cube root of 5 times 5 times 5. Well, it's not wrong to actually go 5 times 5 times 5, which is 125. You then get something I think is more difficult. Because then you got to ask yourself here, okay, what's the cube root of 125? Which means, what number times itself 3 times equals 125? Well, there's a number right there. 5 times 5 times 5. So it's kind of silly to go to this step here. I can just see this answer must be 5. Because again, this here means what number times itself 3 times equals 5 times 5 times 5? Well, that number must be 5. I can literally see that factor repeating 3 times. And remember, just one of these numbers is the cube root. But again, not wrong at all to change this to the cube root of 125, but then you just kind of go back to this 5 anyways. All right, last one. Label each as a perfect square or a perfect cube or neither. For example, for 10,000, is that a perfect square or perfect cube? One, that's not a bad idea at all. So if you go to a calculator, I'll go to a calculator. If I type in the square root of 10,000, I see 100. So I know 100 is a perfect, sorry, I know 10,000 is a perfect square because its square root is a nice clean whole number, 100. Whereas if I type the cube root, let me try the cube root. So every calculator is different. The cube root of 10,000 is 21.5443 blah blah blah. And so as soon as I see that, I know my cube root is not a whole number. It's what we call an irrational number. And so 10,000 is a perfect square, but it's not a perfect cube. And so I'm going to just label this as a perfect square. I might as well just write down the square root of 10,000 is 100. Sorry, it's 10. No, is 100. Yeah. 64 is both, because hopefully we don't need a calculator to know that the square root of 64 is 8. But the cube root of 64 is also, is 4. 4 times 4 times 4 is 64. And if I go to my calculator again, I'll clear all this. Again, square root of 64, I hope you don't need a calculator to know that. But if I type in the cube root of 64, notice I get another nice clean whole number. So 64 is both a perfect square and a perfect cube. So I'll say it's both. Negative 64. Now we got to be careful. The square root of negative 64 does not equal 8 or negative 8. The square root of negative 64 is not a real number. Again, if the answer was 8, well, 8 times 8 is 64, not negative 64. And negative 8 times negative 8 is positive 64, not negative 64. So in essence, if we're dealing with real numbers, the square root of negative 64 is not possible, which is why your calculator should give you an error. If I clear these, square root of negative 64, it says undefined. So it is something we call an imaginary number, actually, that we look at in post-secondary. So you don't actually, for all intents and purposes, as long as you're taking a math course in a secondary school, you can just basically imagine that the square root of a negative number is not possible. Not with a real number, we say. But it is, so it's definitely not a perfect square. However, it is a perfect cube, because the cube root of negative 64 is negative 4. And that's because negative 4 times negative 4 times negative 4 is negative 64. And so this is a perfect cube, but not a perfect square. And notice again those negatives. And when you're dealing with perfect squares, once you see a negative number is never going to be a perfect square. But a negative number might be a perfect cube. And that's all it goes down to. When you have a negative number times itself twice, it's always positive. But a negative number times itself 3 times is negative again. All right, so lastly though, what if we don't have, constants? What if we have variables? And so AB times AB. Is this a perfect square or a perfect cube? This is a perfect square. So how do I know that? Well, kind of goes back to something I mentioned before. I can rewrite AB times AB as a, well, actually I don't even need to rewrite it. I can actually just see right here that I have the same factors repeating twice. And so I can now say, therefore, I can say the square root of AB times AB, it's a little bit neater, must be AB. Right, just one of those. Now if that sounds strange, imagine I gave you instead 5 times 5. The square root of 5 times 5 is 5. So the square root of AB times AB is AB. I appreciate if it sounds a bit stranger, but it is the same idea. It's the exact same idea. But it's not a perfect cube, because there's no way I can have these variables in 3 different groups. Sorry, 3 groups that are the same. If I look at the next one, a squared times b cubed. This is a perfect cube. How can I show that? Well, let's look at the factors. If I take a squared b cubed and write it like this, if I were to write it as a times a, I'll literally write it all out. A times a times a 6 times b times b times b. Okay, think back to when I used the prime factorization. I can write this in any order I want. So I'm going to write it in groups like this. I'm going to write it as a times b. Oh, yeah, I'm recording something right now.
Oh, you're recording.
Yeah.
Okay, sorry.
Sorry. Times a times a times b times a times a times b. Notice all I've done is change the order. But now I've changed the order so that I can see I have the same factor 3 times. And that's how I know it's a perfect cube. It's very similar. It's essentially the same idea as what I did right here. Except this time I was using, a constant, 216, so I broke it up the factors that I knew. In this case, I'm doing the same idea with variables. And so I can then say the cube root of what I started with, a to the power of 6 times b to the power of 3 must equal a times b, or a squared b. Okay? Definitely getting trickier, but it's all the same idea. If we understand what a perfect square and a perfect cube are, and we understand what factors are, then what I'm doing here shouldn't seem quite so weird. Although, we start off with things that I know you'd seen before in grade 7 or grade 8. I don't assume you'd seen this before. Last one. This is actually both a perfect square and a perfect cube. How can I show it? Well, first I'll say, just type right in here, it's both. So first let me write it like I did before as a times a. I'm literally going to list them all out. 1, 2, 3, 4, 5, 6, and then b's. So it is both a perfect square and a perfect cube, which means there's a way I can split this up into 2 equal groups or 3 equal groups in terms of factors. So in terms of 2 equal groups, if I make it as a times a times a times b times b times b, 2 groups of this, notice it's all the same factors. Yes, they're in a different order, but it doesn't matter what order you multiply. This is what tells me it's a perfect square. However, I can also rearrange it like this, as a times b 3 times. And that's what tells me this is also a perfect cube. Tricky question. And again, all I've done is I just took what a to the power of 6 times b to the power of 6 means is by listing out all the factors and found ways to put them into 2 equal groups or three equal groups. Because I can find 2 equal groups, that tells me it's a perfect square. Because I could find 3 equal groups, it's also a perfect cube. And so to finish it off, then I can write these with statements like this. I could say the square root of a to the power of 6 times b to the power of 6, that's a weird looking 6, there we go, equals a times a times a times b times b times b. Or, why not write these with exponents again, a to the power of 3 times b to the power of 3. And because I also said it was a perfect cube, I could say the cube root of a to the power of 6 times b to the power of 6 is the same as a times b times b. Just one of these, which again, if I write with exponents, I get a squared b squared. So, from starting off with reminding what factors are with a, pretty simple equation, 2 times 5 equals 10, and ending off with some, pretty complex things, but it all builds upon the same ideas. Okay, so with that said, I'm going to stop this here.